When calculating the maximum rated of branch circuit short circuit devices where starting current is a concern, conductors must be sized to the values obtained using Table 430.52, but not to exceed the ampacity. This is because the starting current of a motor can be significantly higher than its running current, and the conductors need to be able to handle this higher current without overheating. Table 430.52 provides the minimum ampacity of conductors for motors based on their horsepower and voltage, taking into account the starting current. By sizing the conductors to the values obtained from Table 430.52, you ensure that the conductors will be able to handle the starting current of the motor without overheating, and that the branch circuit short circuit devices will be properly sized to protect the circuit. Motor conductor sizing is a critical aspect of electrical installations, ensuring the safe and reliable operation of motors. Several sections of the National Electrical Code, or NEC, address this topic, most notably Article 430, which covers motors, motor circuits, and controllers. Understanding and applying these rules correctly is essential for electrical professionals. The fundamental principle behind motor conductor sizing is that the conductors must be able to carry the motor's full load current, which is the current the motor draws when operating at its rated horsepower and voltage. However, the NEC also recognizes that motors draw significantly high current during starting, often several times their full load current. This inrush of current, known as the starting current or locked rotor current, can last for a few seconds, and the conductors must be able to withstand it without overheating. To determine the appropriate conductor size, you need to consult specific tables and sections within Article 430 of the NEC. Firstly, you'll need the motor's nameplate information, which includes the horsepower, voltage, and full load current. This full load current is the starting point for your calculations. Next, you'll refer to NEC Table 430.248 for single-phase alternating current motors, or Table 430.250 for three-phase alternating current motors. These tables provide the full load current values for various horsepower and voltage ratings. If the motor's nameplate full load current differs from the table value, you use the nameplate value. With the full load current established, you'll move on to NEC 430.22, which addresses the minimum conductor ampacity. This section requires that the conductors supplying a single motor have an ampacity of not less than 125% of the motor's full load current. This 125% factor accounts for the continuous nature of motor loads and provides a safety margin to prevent overheating. For example, if a motor has a full load current of 20 amps, the conductors must have an ampacity of at least 25 amps, calculated as 20 amps times 1.25. In situations where a motor is started frequently or operates on an intermittent basis, the NEC allows for adjustments to the conductor ampacity based on the motor's duty cycle. These adjustments are outlined in NEC 430.22e. However, for most typical motor applications, the 125% rule applies. Now, let's consider the short circuit and ground fault protection for the motor circuit. This protection is typically provided by a circuit breaker or fuses. NEC 430.52 governs the maximum rating or setting of these overcurrent devices. The purpose of this protection is to protect the motor, the conductors, and the equipment from damage due to short circuits or ground faults. The maximum allowable rating or setting of the overcurrent device depends on the type of device used, as well as the motor's design and application. For inverse time circuit breakers, which are the most common type used for motor protection, the maximum allowable rating is typically 250% of the motor's full load current. This higher percentage is allowed because the circuit breaker must be able to withstand the motor's starting current without tripping. However, if this 250% value does not allow the motor to start, the NEC permits increasing the circuit breaker rating, but not to exceed 400% of the motor's full load current. For fuses, the maximum allowable rating varies depending on the type of fuse. For example, for dual element, time delay fuses, the maximum rating is typically 175% of the motor's full load current. This lower percentage is due to the fuse's ability to withstand temporary overloads such as the motor's starting current. If this 175% value is not sufficient to allow the motor to start, the NEC permits increasing the fuse rating, but not to exceed 225% of the motor's full load current. It's important to note that these are maximum values, and the actual rating or setting of the overcurrent device should be selected based on the specific motor and application. The goal is to provide adequate protection without causing nuisance tripping during motor starting. Now let's address the specific question about whether conductors need to be sized to values obtained using NEC 430.52 when starting current is an issue. The answer is yes, but with a crucial caveat. While NEC 430.52 primarily deals with the rating of the overcurrent protection device, it indirectly impacts conductor sizing. The conductors must be sized to handle the motor's full load current as well as any potential overloads without exceeding their ampacity. Therefore, when selecting the overcurrent protection device based on NEC 430.52, you must ensure that the conductors are adequately sized to handle the current that the overcurrent device will allow to pass. In other words, the conductor ampacity must be equal to or greater than the motor's full load current multiplied by 1.25 as per NEC 430.22, and it must also be sufficient to handle the maximum current that the overcurrent device is rated to carry. For example, if a motor has a full load current of 20 amps, and you select a circuit breaker with a rating of 50 amps, based on NEC 430.52, the conductors must have an ampacity of at least 25 amps, calculated as 20 amps times 1.25. However, the conductors must also be able to safely carry 50 amps, which is the rating of the circuit breaker. In this case, you would need to select conductors with an ampacity of at least 50 amps. This ensures that the conductors will not overheat or be damaged if the motor draws excessive current. Now, let's consider the situation where the motor's starting current is particularly high, and the selected overcurrent device rating is close to the maximum allowed by NEC 430.52. In such cases, it's even more critical to carefully select the conductor size to ensure that it can handle the potential overload. You may need to use larger conductors than initially calculated based solely on the motor's full load current. To determine the appropriate conductor size, you can consult NEC Table 310.16, which provides the ampacity of various conductor sizes based on their insulation type and installation method. You'll need to select conductors with an ampacity that is equal to or greater than the maximum current that the overcurrent device is rated to carry. In addition to the conductor ampacity, you also need to consider the voltage drop in the motor circuit. Voltage drop is the reduction in voltage that occurs along the length of the conductors due to the resistance of the conductors. Excessive voltage drop can cause the motor to operate inefficiently, overheat, or even fail to start. The NEC recommends limiting the voltage drop in motor circuits to a maximum of 5%. To calculate the voltage drop, you need to know the length of the conductors, the conductor size, a motor's full load current, and the voltage of the circuit. There are various online calculators and formulas available to calculate voltage drop. If the calculated voltage drop exceeds 5%, you'll need to increase the conductor size to reduce the resistance and lower the voltage drop. In summary, when sizing motor conductors, you need to consider the following factors. Firstly, the motor's full load current. Secondly, the 125% factor for continuous motor loads. Thirdly, the maximum rating or setting of the overcurrent protection device based on NEC 430.52. Fourthly, the ampacity of the conductors based on NEC Table 310.16. And fifthly, the voltage drop in the motor circuit. By carefully considering these factors, you can ensure that the motor conductors are adequately sized to handle the motor's full load current, starting current, and potential overloads without overheating or causing excessive voltage drop. This will help to ensure the safe and reliable operation of the motor. Always consult the latest edition of the National Electrical Code in any applicable local codes for the most up-to-date requirements. Motor control circuits are also vital parts of motor systems. These circuits use lower voltage power to control motor starting, stopping, and speed. The conductors in motor control circuits must be protected against overcurrent, but the rules for this protection are different from those for motor power circuits. NEC Article 430 Part 7 covers the protection of motor control circuit conductors. The rules vary depending on the specific control circuit and its application. In general, the overcurrent protection for motor control circuits is sized to protect the control circuit conductors from overloads and short circuits, but it's not intended to protect the motor itself. The overcurrent protection for the motor is provided separately as discussed earlier. When sizing motor conductors, it's crucial to consider the ambient temperature in which the conductors are installed. The ampacity of a conductor decreases as the ambient temperature increases. This is because high temperatures cause the conductor's insulation to degrade more quickly, reducing its ability to dissipate heat. NEC Table 310.16 provides the ampacity of conductors at an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds this value, you must apply correction factors to reduce the conductor's ampacity. These correction factors are provided in NEC Table 310.15. For example, if the ambient temperature is 40 degrees Celsius, you may need to reduce the conductor's ampacity by 8%. In addition to ambient temperature, you also need to consider the number of conductors bundled together in a raceway or cable. When multiple conductors are bundled together, they generate more heat than if they were installed separately. This increased heat can reduce the ampacity of the conductors. NEC Table 310.15 provides adjustment factors for the number of conductors in a raceway or cable. For example, if you have 4 to 6 current-carrying conductors in a raceway, you may need to reduce the conductor's ampacity by 20%. It's important to note that these adjustment factors apply only to current-carrying conductors, which are conductors that carry current under normal operating conditions. Grounding conductors and neutral conductors that do not carry current are not considered current-carrying conductors. When sizing motor conductors, it's also essential to consider the type of insulation used on the conductors. Different types of insulation have different temperature ratings. The temperature rating of the insulation indicates the maximum temperature that the conductor can withstand without degrading. NEC Table 310.104 provides a list of common insulation types and their temperature ratings. For example, THHN insulation has a temperature rating of 90 degrees Celsius, while THW insulation has a temperature rating of 75 degrees Celsius. You must select conductors with an insulation temperature rating that is equal to or greater than the maximum temperature that the conductors will be exposed to in the application. When sizing motor conductors for specific applications, such as motors used in hazardous locations, there may be additional requirements. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. The NEC contains specific requirements for electrical equipment and wiring in hazardous locations in Articles 500 through 516. These requirements are designed to minimize the risk of ignition in these areas. For example, in some hazardous locations, you may be required to use explosion-proof enclosures for motors and other electrical equipment. You may also be required to use special types of wiring methods, such as rigid metal conduit or mineral-insulated cable. When sizing motor conductors for these applications, you must follow the specific requirements outlined in the NEC for hazardous locations. Another consideration when sizing motor conductors is the type of motor being used. Different types of motors have different starting current characteristics. For example, some motors have very high starting currents, while others have relatively low starting currents. The starting current of a motor can affect the size of the conductors required. For motors with very high starting currents, you may need to use larger conductors to handle the inrush of current without overheating. You may also need to use special types of overcurrent protection devices that are designed to withstand high starting currents. In summary, sizing motor conductors is a complex process that requires careful consideration of several factors. These factors include the motor's full load current, the 125% factor for continuous motor loads, the maximum rating or setting of the overcurrent protection device, the ampacity of the conductors, the voltage drop in the motor circuit, the ambient temperature, the number of conductors in a raceway, the type of insulation used in the conductors, the type of motor being used, and any applicable requirements for hazardous locations. By carefully considering these factors, you can ensure that the motor conductors are adequately sized to handle the motor's full load current, starting current, and potential overloads, without overheating or causing excessive voltage drop. This will help to ensure the safe and reliable operation of the motor and the electrical system. Remember to always consult the latest edition of the National Electrical Code and any applicable local codes for the most up-to-date requirements. Consulting with a qualified electrical engineer or electrician is also highly recommended to ensure that the motor conductors are sized correctly and that the electrical installation meets all applicable safety standards.